Energy is a substance that can do stuff. Ancient biomass like plants, animals, and dinosaurs that have turned into oil. We see it in many forms all around us to power our lives and our bodies. Where does all this energy come from? We'll cover that a little later, but first, let's see how energy changes form. Food gets broken down in our gut and passed to all our cells where mitochondria transform the food bits with oxygen to generate ATP. Mitochondria are the energy factories of our bodies. With this chemical energy transferred from our gut to our muscles, we can now do stuff. Muscle chemical energy is converted to motion, kinetic energy. As the ball slows down, it loses kinetic energy and gains potential energy. It stores energy relative to the ground, and on the downward path, energy is converted back to kinetic. Another form of kinetic energy is hydropower. Water moves a turbine, and the turbine is connected to a generator. The kinetic energy of the water produces a changing magnetic field in the generator that's converted into electrical energy by moving electrons in a conductor. Current flowing in high power transmission lines gets to your house, so you can turn on some lights. And the ultimate light bulb is the sun. Almost all the energy we get here on Earth comes from the sun. Solar energy is stored as chemical energy in plants in the form of carbohydrates, sugar. After millions of years, biomass is compressed into oil. We then pump that out of the ground, refined into gasoline that we use to power our cars. The sun causes another form of energy. It heats Earth's surface unevenly, often because of cloud cover, which causes movement of air molecules from the differences in air pressure. As warm air rises, cooler air moves in to fill the space. The wind can spin the blades of a generator similar to water moving a turbine. The motor inside rotates a magnetic field that induces an electric current that we tap into on the power grid. And there's another type of electric energy nearby. It starts in the clouds. Moisture molecules and ice crystals in clouds rub together, creating a buildup of charge, negative on the bottom and positive on the top. In response, there's an accumulation of positive charge on the ground. When these charges get really large, there's a violent discharge of energy. It's like a mega battery in the sky. But batteries work a little differently. Let's take a look inside. A battery has two different metals that releases electrons differently. The top part is the anode and is made up of powdered zinc metal most commonly. It's kind of gooey. The cathode, connected to the bottom of the battery, is on the inside of the case and is a combination of manganese dioxide and carbon. The anode has a higher potential, so it drives a current when connected to an external load like a light bulb. The battery is converting stored chemical energy into electrical energy. This is a good time to explain the difference between power and energy. Power is how much work can be done, like a car engine with 500 horsepower or a speaker with 200 watts. Electrical power, like our humble battery, is voltage times current. This battery is 1.5 volts, and let's say for our light bulb it draws 0.1 amps. That's a total power of 0.15 watts. Energy is just how long you can sustain a particular power level, power multiplied by time. For our battery, that's 0.15 watts times, say, 2 hours, which is 0.3 watt hours. For comparison, a typical dishwasher cycle uses 1,000 watt hours or 1 kilowatt hour. So we've now seen where all of these forms of energy come from, the sun. But where does the sun get its energy? The sun is mostly hydrogen with some helium as hot charged particles called a plasma. Under the enormous pressure, because the sun is so massive, the nuclei of hydrogen are squeezed into larger helium atoms and release a whole lot of energy in the process. That's nuclear fusion. Now we can tackle E equals mc squared, Einstein's most famous equation. E, as you may have guessed, does indeed represent energy. But what about m and c? C is the speed of light, a really big number, and m is mass. But Mass of what? In the sun's fusion process, mass of the newly formed helium is slightly less than that of the original hydrogen nuclei. Some of the mass was released as energy. The difference in mass is what we plug into the equation to calculate how much energy is converted. Let's do an example. If we converted 1 teaspoon of hydrogen nuclei to energy, how much would that be? At the depth where fusion starts in the sun, 1 teaspoon would have a mass of about 100 grams. That's about the weight of 4 AA batteries. So plugging into E equals mc squared, we have 100 grams of mass. Speed of light is 300,000 kilometers per second. That's 9 trillion joules of energy. A joule is the amount of energy in the metric system. That's equivalent to 2.5 billion dishwasher loads, or the energy of 2,500 coal-burning plants in 1 hour. E equals mc squared is the ultimate in energy conversion. Where does the energy in hydrogen come from? We'll get to that at the end. But first, there's another kind of nuclear energy, fission. It's how nuclear plants generate power. This process starts with a neutron colliding with a massive nucleus like uranium. It splits into 2 smaller nuclei, some energy, and a few neutrons. These neutrons trigger more uranium collisions, a chain reaction that generates lots of heat, millions of times more energy than any chemical reaction. If we put these nuclei in a shielded reactor, regulated by control rods, we could harness this massive energy. The thermal energy produced by the nuclear reaction could be directed to heat water to steam. The steam then drives a turbine, converting the energy to kinetic, that is connected to a generator, you've seen this before, which provides electrical energy on the grid that we use to power our stuff. Energy is never created or destroyed, it just changes form. All the energy on Earth will eventually radiate to outer space. Where does it come from? All the forms of energy we've seen started with the sun. Hydrogen nuclei formed shortly after the Big Bang, storing energy in a compacted quarks inside the neutrons and protons. The first stars formed 200 million years later in the early universe. Do you know how we could capture all the energy from the sun? Click on this video to find out.